Good morning, everyone, and welcome to today's webinar, Build Voice-Enabled Devices with Alexa. My name is Ted Karzewski, Content Marketing Manager for the Alexa Voice Service, and I'll be the moderator today. Before we get started, I'd like to go over a few items so you know how to participate in today's webinar. As an attendee, you can listen in using your computer's speaker system by default. If you would prefer to join us over the phone, simply select Telephone in the audio pane and the dial-in information will be displayed. During this webinar, you'll have the opportunity to submit questions to today's presenter by typing them into the questions pane of the control panel. You may send in your questions at any time during the presentation. We will collect these and address them in the live Q&A portion of the webinar. I would now like to introduce our presenter for today. Matt Tavis, Principal Solutions Architect on the Alexa Voice Service team here at Amazon. As the Principal Solutions Architect, Matt works with OEMs, ODMs, and hardware and software partners to provide architectural and technical guidance throughout Alexa integration. Matt has been with Amazon since 2005, and he has worked with Amazon Web Services offerings throughout his tenure. So I'll hand it over to Matt to take it from here.
Thanks, Ted. I appreciate it. I'm hoping everyone can hear us well. Feel free to raise your hand if you're having trouble with the audio, and we'll watch the message board and the chat windows for any messages from you. But I'd like to obviously thank you all for attending today. Really appreciate you taking time out of your busy day to listen to more info about how the Alexa Voice Service can be used. As Ted mentioned, I'm a solutions architect, and I've been lucky enough to be with Amazon for the last 11 years. So obviously this latest journey with Alexa is my latest stop inside the Amazon family, but I'd love to tell you more, and hopefully you'll learn some tidbits along the way. So what to expect from this session today. We're obviously going to start by setting the stage. Many of you may very well be familiar with AVS and Alexa, but I do want to make sure we establish the entire ecosystem and our vision. After that, obviously we'll dive into one half of the Alexa set of services, the Alexa Voice Service, and understand more about that. We'll talk about AVS client implementation, how to implement it, some tips and tricks, things to use along the way, as well as focusing on some of the components of a hands-free solution, which is obviously something that many of our developers are excited about, the ability to bring the hands-free magic of Alexa to their devices. And then we'll finish up with some discussion around development kits for AVS and things to help you get started. So first off, obviously I'm not saying anything you probably don't already know, but I think Alexa is established, and one of the things we're discovering is that voice is a key component of the future. It's a very natural interaction. It's been around obviously for thousands, hundreds of thousands, potentially many years beyond that, people interacting via voice. And Alexa has really established that capability of this interaction to be a natural human-style interaction with devices, and both the Echo and then whatever third parties might develop on top of the AVS platform. We really see this as a first-party interaction mechanism that developers and customers can use so that they can interact more naturally with the devices. Obviously, is one of many modes of interaction, but definitely voice is here, and it's here to stay as a natural interaction model. And so seeing how you can bring that to your technology, your devices, and your products, something every company should consider as they go looking at their strategic roadmap going forward. Obviously, as we have done a lot of work in this space. The Echo really kind of helped, sort of cement voice as a natural interaction model in many ways, and help sort of establish this is a sort of a paradigm shift from a user interaction perspective. The original Echo, this is actually Gen 2 pictured here, but the original Echo has already received now over 48,000 customer reviews with a 4.4 star rating. And many folks talk about not only what it has done to date and how it came out, but also the potential of what it might lead to. And I think that's a key component. That's definitely where you feature. What's our development community going to provide and build on top of this set of services going forward that really is going to continue to grow this market. The Echo being what you might call a reference design. whereas others are going to build and grow upon that technology. And so that's where we're looking to you and to the ecosystem in general to expand and grow that. So let's talk about sort of the Amazon Alexa platform and the vision. The goal here, in many ways, is to think about Alexa as always getting smarter. Alexa, started as it was that speaker, that wireless speaker that you could speak with, that had some basic capabilities in terms of knowledge, in terms of timers, and in terms of playing music. But the goal here is not just to stop there, but rather continue to expand that intelligence, both through our own additions of new content, new capabilities, new smart home skills, but also through the integration with a larger ecosystem of partners and products and providers that are going to bring intelligence to that platform, leveraging the voice interaction that Alexa provides, but continue to allow others to expand that from a content as well as product perspective, so that Alexa is always getting smarter, and that really is the intention and the goal. Behind the Alexa platform, as many of you know, is this cloud-based voice service. It's many domains have been defined, as we see here. Cloud-based intelligence, weather, timers and alarms, smart home control. Recently, we added locks to the smart home skills kit. Had lights and light bulbs and switches prior to that, and obviously we'll continue to expand their music, news and information, and of course shopping. All of these are domains or areas that Alexa can interact with their users, but then the goal is obviously to continue to expand this over time. And really, that's on the skills and knowledge perspective, and on the vision side in terms of hardware and the exposure of Alexa to our customers, to our shared customers, is really to put Alexa everywhere. So there's no reason why Alexa couldn't, fit in many of these categories, and in fact already is. Beyond the Echo family of products, Alexa already is in many other locations in the home audio space. TV and video, smartphone apps, wearables. We have several watches in the market today that are developed by third-party companies that are using the Alexa voice service as a mechanism for interaction. There's been several announcements and developments in the automotive space as well. Thermostats, obviously from a smart home skills control, home security locks have been added, appliances, large and small, and of course even the development space, maker boards. The Raspberry Pi project has been very successful in terms of getting many folks involved in building and developing with the Alexa voice service platform, and that's obviously something we want to continue to support. A really big piece is not just our own innovation, but allowing you as the developer to innovate for our shared customers as well through the development of new technologies and new capabilities. And that really is the vision of Alexa. She should be omnipresent in many locations, in many devices, in many areas around daily life. And it's really built up, when you think of Alexa, there's sort of two halves. We've sort of danced around it a bit. I think it's time to sort of dive in a little bit more. Two powerful frameworks. One is the skills kit, right, which is how to create custom content, custom experiences, integrate smart home capabilities, create your own flash briefing services, add your own smart home skills for your own smart home devices, obviously create custom skills that integrate with services, external services, or even content capabilities. So the skills kit is one piece. It is an easy, natural extension point that allows a developer to quickly build a new skill based on several templates we make available, and then go ahead and customize that. And as you've seen, the growth in that space has been tremendous. Over 10,000 skills published so far in the U.S. alone. That continues to grow actively. What I focus on is the other half of it, and that's what we're going to spend more time talking about today, which is the Alexa voice service, which is allowing you to develop and build devices and applications that then tie into this, if you will, Alexa service platform, so that your device with a mic and a speaker can become another endpoint in that ecosystem of products and content. So you can take a new piece of hardware, a new design you're building, add that mic array, add the speaker, and then all of a sudden you can then access those same skills, the core platform, of course, with music and timers and alarms and calendars. But then on top of that, you can also tie into the Alexa skills kit and have access. So any of your Alexa-enabled devices have access to the same platform and ecosystem that all these other skills are enabled upon all the Echo family devices use. So it's a great way to participate as another member of that Alexa Anywhere vision and be another useful extension to the Alexa platform and ecosystem. And we've continued to expand that. Obviously that's, the US is where everything started, but as many of you have seen, we've expanded recently into the United Kingdom and Germany, and the Alexa Voice Service is also now available in the United Kingdom and Germany as well. So now you can build skills that are targeted for multiple languages. You can build devices that can operate in multiple regions with multiple different Amazon customer marketplaces and accounts. And so this is something when you build, you can design for multiple regions and roll out internationally. And of course, as you imagine, this is just the beginning. As we continue to roll this out, this is something we'll be rolling out in many more locations around the world. But fundamentally, that is kind of the beginning of where we started, and we're going to continue to expand that platform. So now there's a couple aspects to think about. So let's dive in a little bit more on the voice service. So there's two big aspects to when you're building a voice-enabled product. One is what's handled, obviously, by the platform. What can you effectively take for granted it's going to be there? So all of the aspects of the domains, like, what is music versus, what is a custom skill versus what is weather versus what is a timer and alarm, that's part of that product platform. We route the requests coming from your devices appropriately, so they actually are handled properly by the platform and the service. The next, of course, is in speech primitives. So the ASR, automated speech recognition, NLU, natural language understanding, TTS, text-to-speech, EV, which is more of a knowledge content platform and how to look up content. All of those things are part of that platform. So when you're streaming audio from your device to the Alexa service, we handle capturing all those, which means we also handle capturing it in multiple languages, as I mentioned before. So your device can just simply stream audio, whether it be in English or German. We can handle both of those and understand what you're targeting and what how to map that to an actual intent. And how we map those from a platform services perspective. On the developer side, so your responsibility is really around the device components. Making sure you have the hardware installed correctly. You have a mic array in there, you have a speaker for output. You have the audio algorithms that are necessary for your device. So if you do go down the wake word path, or the far field, as we call it, path, where you're receiving user audio with a wake word and then capturing it in perhaps a noisy environment, handling front-end algorithms around noise cancellation, echo cancellation, noise reduction, and tying all those pieces together. That fits in the developer side, as well as then deploying and installing and updating that Alexa voice service client. We give you a lot of support and examples there, but obviously maintaining that on device is something handled by the developer. So those are the two sort of halves, if you will, of building a product with AVS. And there's multiple types of interactions, multiple types of devices you could build. We have two sort of families, if you will, touch-initiated devices, where there's physically a hands-on interaction. So there's a kind of a push-to-talk, where you push and hold that button or soft button on the device and interact with it. And then there's more of a tap-to-talk, and you see these mapped to the Echo family of products. But for example, tap-to-talk is very common in our AVS-enabled smartphone apps. You tap it and then you speak, and then the Alexa voice service will detect the end of that and tell you when to stop listening. It's also true in our smartwatch integrations. There's a couple of smartwatch integrations that use a tap-to-talk interaction, where you tap, speak to it, and then it captures the audio and streams it up, and then stops listening when it gets a directive to stop. And that's what we mean by this cloud versus client endpointing. Endpointing is the detection of the end of speech. If it's a held button, it's obviously done by the device. If it's actually a tap or a wake word, the cloud, as in the AVS service, will tell you when to stop listening. The other half, beyond touch, is the voice initiated. This is the wake word, so how you're used to interacting with the Echo and Echo Dot. And now, recently, the Amazon Tap supports this as well, where you simply say the wake word, Alexa. And I apologize for anyone's Alexa that might have just woken up. You say the name, and all of a sudden, she responds, wakes up. And there's many interactions there. Headless devices, could light up. They could also make, in some scenarios where there's no visual affordances, they can make, Bing noises like ear cons, as we call them, but many interaction approaches there, or even lighting up screens. That can be anywhere from, say 5 to 10 feet, which you might call a near field interaction, to 20 feet or across the room, which you might call a far field interaction. Those are many approaches that exist today, and those are sort of things that you think about when you're building that product. Which category do I want to work into? And we'll talk more about the wake word work involved later on in the deck. So let's dive in now a little bit into the API itself. So there'll be more detail here coming up, but the two big things you need to know is there's two parts. One is, there's the API you speak to, and obviously there's the dot right there, but this could be, a Raspberry Pi development kit. It could be your final product. They all operate the same way. So directives are messages sent from the Alexa voice service to that client. So a play directive is a common one. So you ask Alexa play music, you're going to get a play directive, which will include the metadata to act on that directive. Set alert a directive is when you ask for a timer, you're going to get a set alert directive. So the directives mapped to the various domains and actions you should take. Speak directives tie you to here's what to say or what to play through your speaker. And then there's events. These are things that you send from the device back up to the Alexa voice service. Events could be things related to I've started playback, I've finished playback. If you have a pause button on the device, you might say you paused, things like that. You also can then report progress activities. So I'm progressing in the playback of music, which is part of the audio playback model. Those are events that are then bubbling up from the device. So let's take a dive through how this might play out in a little bit more detail. So if you say Alexa play music, the first is that wake word engine is going to capture the name Alexa. Play music will just follow through as part of the speech capture. And then once it lights up, it'll start capturing that rest of that utterance, which is the play music piece. You send that as a event, which is the recognize event, to the speech platform. So you feed us the PCM audio. It's a 16-bit, 16 kilohertz PCM audio format that you then send as part of the recognize event. That then gets handled through the various layers of the speech platform, or the voice service platform. The first is speech recognition. It determines you said play music. Then it does language understanding and says play music is going to map to the music domain, and it's to play something default. If you said play Bob Marley, that's different. It would specifically add that metadata. Now the intent is to play music. It then forwards that to, generally I'm calling it skills here. It could be skills or specific internal domains. It says, hey, I need you to play music. When that skills or capabilities of the music service, it picks a piece of music for you based on what you might like. This is tied to your Amazon account, so it has information about what you like and what you play. That then generates a directive to say, hey, we need to play this. And then two pieces come back, not just the play directive, but also the text-to-speech. So Alexa will then also do okay, here's some music by, or here's something you might like, and they will actually, the text-to-speech service will encode that text into an MP3 that's embedded in the response. So when you get back, you're going to get a voice response from Alexa. It's including not only the speak directive, which will be the intro, saying Alexa, Alexa's intro to the music, which you will play through the speaker, but you'll also get a play directive, which will say, and here's the song from this particular music service to start streaming. So that's that whole flow and how that functions. As you can see, from a client perspective, it's fairly well captured in I stream some audio up, I get a couple pieces, I get a piece of audio back, and then I get a directive to start playing. So fairly captured. You can imagine a lot of interactions look very much like this. A speech to text, a text to speech speak directive that gives you some audio to play, and then maybe a follow-on action to take. So much of the interaction feels very much like this. Now, there's lots of interfaces in the AVS API if you've read the docs. The big ones to note are obviously the speech recognizer. That's where you get the recognize event. You'll see alerts is in there. Alerts is for managing timers and alarms. It's about setting an alert, deleting an alert, sort of managing those based on user utterances, or even companion app interactions where the companion app can cancel an alarm. You'll get a directive on that. the audio player interface, which is all about, playback control. So when the user says next, it sends you the directive to do that. The playback controller is really about the affordances locally on the device in terms of the buttons and volume controls. The speaker itself in terms of muting and unmuting, things like that, setting the volume itself. System, and then which is more client-specific info, and then settings, which recently was added as a new interface to handle the locale information for which endpoint you should be using based on the user account you're linking to. So interacting with the cloud service, it seems like, it sounds like it's very much an API, right? It's an API endpoint, in this particular case, the North American endpoint, AVS Alexa and Amazon.com. However, it's an endpoint that has a few different interesting wrinkles, right? You've got the events and directives, which are coming back and forth. You see those coming down. And so which ones you're getting is really depending on what audio is in it. So a single recognized event could generate one or more different types of directives. So in many ways, it's not just an API endpoint, but rather also a message bus. So you have to think about what types of messages could come down. They could come in many different orders. And as time changes, as time evolves, as we add content to the platform and capability, you might get new directives and new events that just start appearing. So there really is a sort of a flexibility that's required from a client perspective to understand how these things can occur. And really it's an API endpoint, but there's a message bus sitting on top of that. And then there's even a little bit of a state machine baked into the whole thing. A lot of this is obviously well defined, if you will, and shown in the docs, but also even in the Java sample app. There's a state machine to determine what do you do when you've got music playing, the user interrupts to say something and ask a question, and an alarm fires at the same time. So there's some state machine components as well. So thinking about how you then stream those bits of audio together and which ones take precedence, all defined in the documentation. So there's actually a few layers beyond a simple API to consider as part of that. And all that is identified as part of the Java sample app, and it's also in the docs. But there's definitely a few pieces beyond just the simple API request response model. And there's even a down channel, which I'll talk about in a minute here as well. Now this is an example AVS client architecture. I could obviously spend probably the next 20, 30 minutes just on this picture alone. I won't do that. Hopefully we are recording this session, so it'll be available for pausing later or screenshotting right now. But really the way to think about it is a few key pieces that are part of a complete AVS client. One is on the bottom right, you'll see there's that companion app space. At some level, you have to have a model where you log the user in, give them access, allow them to authorize this device to access their Amazon account. And that's really the companion app piece. We have several samples available. There's a web app, there's an iOS and Android apps as well you can use. And that uses the login with Amazon. That gives you your AVS token use for the rest of your requests and the refresh to continue getting access. Big pieces here, the messaging layer, kind of in the middle there, is really about managing those directives and events, how we dispatch events, how we handle directives coming in. You'll see right below that, there's a connection management component. That's where you handle the HTTP2 piece. That's an important one. Alexa Voice Service does use HTTP2 as its interaction model. And that, for those of you not familiar with it, HTTP2 is both a up and down channel for request response over HTTP, but then also a explicitly down channel that the server holds open to send messages out of band at any time. So, for example, if I cancel an alarm from my companion app, I have to have a way to send a message to the client, to the device, that there's something happened on the companion app to set volume, pause, cancel an alarm. That down channel is used for sending messages down. So it's a little bit beyond the standard HTTP type connection. So you'll have to pick libraries for that. And we have some samples and pointers in that in the docs. And then there's really a controller layer, which deals with how to send messages out to alert management, how to store alerts, how to then interact with the audio player, which will then be a local component. Not every device has the same media player capabilities. So, picking a media player that works on your platform, whether it be, for Android devices, an Android media player versus, say a GStreamer for, an embedded Linux C++ platform. So, you kind of pick and pick the right device or the right player for that particular platform. And then there's components there that sort of route the information back and forth. And then, of course, if you choose to do that wake word, there's a whole wake word engine piece, which means you're running to feed, to wake up, if you will, the application, say, hey, the user is now talking to you. You don't listen until you hear your name. Once you hear Alexa, now I need to tell the client to start pulling in that audio and streaming it through the recognize event up to the Alexa platform. So there's a few components here that are kind of core to the client architecture and definitely worth spending some time on. This is all part of the Java sample app. You'll see all these pieces in there. So definitely worth going through and understanding how it was built there, because you may choose to do it that way or differently. Now, the first tip I'll mention along the way, and I've kind of harped on a little bit here, but I think it's important. In almost all of my interactions with my partners and customers in terms of helping them understand how Alexa Voice Service works, I almost always point to the sample app. Not because it's production code you should drop into your device, but rather because it actually helps you see what the natural flow and interaction is when interacting with the Alexa Voice Service. It's nice because it's a Java sample app. It can run anywhere. We have a client for, it runs on PC, Linux, Mac, Raspberry Pi, chip. It also includes a hands-free implementation. You use the Sensory wake word or a kit.ai wake word as a mechanism, so you can see the full capability of a AVS client running in almost any platform you happen to be developing on. And that gives you something to compare against. So as you then go build your own solutions or devices, running a test of, here's what I said to my device, here's what I said to the sample app, here's the response, let's look at the messages. The log information that's captured in the sample app has tons of information around the JSON body that was sent up, the body that was returned, so you can see if you've encapsulated all the right information, if all the right same elements are coming back for your device versus the sample app. Definitely important to see there. And it's really the first step in many cases for a lot of debugging scenarios. Am I sending the right data? Am I getting the right data response? Because, as I mentioned before, it's not just a simple API, but also a bit of a message bus on top. So seeing that message flow is important as well. Here's some examples in the logs themselves. A few things that are worth noting. You can see here, this is an example of an event. Up top, you can see a timestamp, but then you can also see the thread ID. This will help you understand. It's obviously the sample app is multi-threaded. In many applications you build would be multi-threaded. You'll have, for example, in this particular case is an event queue thread. It could also be a down channel thread that's listening on the down channel. All those will be identified kind of in that thread ID to help you see how messages are coming in from the various locations, as well as then the event information itself. In this case, this is a classic recognized event. So what's happening here is, somebody has spoken audio, they've woken the device up and they've spoken audio to the device. It's now being captured and being streamed to the Alexa Voice Service, and that's where you see the recognized event being sent up and message IDs. These are useful for, if you do need some more debugging help. It seems, this is important information we could use to look up that message as we process those requests. On the flip side, the directive, you'll see the Amazon request ID. That's an important piece of metadata. If you were asking for help or support through the forums, that request ID can help developers look up what exact requests we saw there, and then how they can then validate what occurred on the server side. In this case, it's a speak directive. You'll see inside the directive body, the name is speak, and that's saying this is what you should send out through your speaker, and that will be Alexa's voice in this scenario. You'll see in this particular, the body of this one will include an embedded MP3 payload. So when Alexa speaks, she sends you MP3s. The Java sample app actually captures that MP3, writes it to a temp file, and plays it through the media player. Now, these sequences get more and more complex, and that's important to realize. Obviously, user interaction by voice is not always what we call, a one-shot. In many cases, it's a multi-turn interaction. So, for example, if somebody were speaking your device and said, Alexa, set a timer, you'd send up the recognized event with the PCM audio. Alexa would say, oh, that's great, but I need more information. She'd say, for how long? Which would be send you a speak directive with the attached MP3, and also an expect speech directive. This is one of the directives that tells you to open the microphone again, that we're expecting the user to say something. We've prompted the user to say something. So you then reopen that microphone, and then you then send up, you obviously, as you're sending up, you'll speak the parts. As you can see, the speech started, speech finished. That's telling Alexa, hey, I finished saying what you asked me to say. That will then open the microphone, and then the user would respond, 10 minutes. You'll send that 10 minutes up, and then, of course, Alexa will tend to say 10 minutes starting now. That's a multi-turn interaction, and worth noting. That's something all devices are expected to support. So this is an example of where there are kind of that message bus model will then drive your device to take certain actions. But you need to continue to report up what's happening as well as respond to those directives as appropriate. Now, if we continue that setting an alarm example, but maybe in a one-shot model to simplify the display, because otherwise we need a bigger screen. I don't have one. So if you say, Alexa, set a timer for 10 minutes, you get the recognize event, and then it says 10 minutes starting now. You'll get a speak directive. You'll say speech started, speech finished. There's no expect speech directive because it's already a completed one-shot command. But then you'll see there's this purple line, and that's the set alert directive. That is actually coming on the down channel. So there's an example of where the speak is happening, but then you're looking for that other directive, like, wait, where am I supposed to do? What am I supposed to do relative to that alert? That'll actually come on a separate channel, not the direct request response, but rather the down channel, and that's where HTTP2 is important. You will get messages not only as a response, but also as the down channel, direct from the server initiated. So that's something you always have to look for and listen for. So there's a few HTTP2 implementations that are out there that are worth noting. If you're in the Android space, OK HTTP is quite common. We use Jetty in the Java sample app. And then there's ng HTTP2, which is often used in the C++ arena, tied into libcurl quite often. Instead of using the raw library, you could use libcurl. So those are multiple implementations that exist to help you with that piece. Once the alert's set, you then you actually would say it's succeeded. And then when it fires, you then will alert, say, hey, the alert has started, the alert's in the foreground. So there's all these pieces that are part of that timers and alarms flow that are required to be implemented as part of that device implementation. The next piece that comes up quite often is music. So when we think about other challenges or opportunities, is when you're talking about music and music formats. That's another piece where beyond just handling different messages, you have to think about encodings of the content that are coming back. Alexa always returns MP3 for her audio. But various music services that you can interact with and enable do provide different formats. So you can see there's AAC MP4, MP3, HLS, PLS, M3U, Shoutcast, and even ID3 tags. So those all are common codecs we see in the music service providers that exist today. And there's even different formats and rates, bit rates associated with those as well. So that is one thing that's part of your testing and development, to make sure to think about how you're going to source the codecs appropriate for the various music providers if music is something you want to enable. And as you can see, Pandora is in that list. Pandora was recently added to the list of music service providers that can be supported with AVS. But as you go down the music format, there's definitely more steps in terms of working directly with us on music services and the enablement. So when you fill out and register your devices, you'll have some questions around music. You'll definitely want to fill those out. And that will key us to the idea that you want to actually enable music, and we'll work with you around what that takes and what the steps are in terms of getting certified to support those music providers. Definitely more work than just integrating with the API there. Music playback has its own, sequence of directives and events that are important to recognize. So if you say, Alexa, play classical music, you're going to get a speak directive that says playing classical music from Amazon Music, and then you'll get the play directive. That play directive will include a URL. When you're streaming the music itself, you're actually streaming from the music provider directly. So those URLs are not back to the Alexa voice service, but rather directly to Pandora, iHeartRadio, TuneIn, Amazon Music, and the locations they store that information. So you'll get a URL that you need to go access from your device directly. So that's actually happening out of band from the Alexa Voice Service integration. But on top of that, you'll have to alert or event to the Alexa Voice Service your progress along that path. So as you're playing and streaming music, you're going to get, as part of that playback directive or play directive, a series of progress event pieces of metadata that will tell you how often you need to report and at what and how soon. So after, say, 20 seconds, you need to report, and then every minute you need to continue to report. And that's this progress. You'll see several events around progress report, delay elapsed, progress report interval elapsed, and then playback finished, nearly finished are also part of that flow. The playback nearly finished event will clue us into the fact that you need your next song, the next piece if it's not a playlist, and that will then be the next play directive we get back. In many cases, we see devices to reduce buffering risk or latency will move that playback nearly finished quite early up in the process so that they get the next song so they can actually start buffering it ahead so there's no block between song 1 and song 2, for example. But that's definitely the series of events that are critical, and this is a process that will have to be validated for certification purposes in terms of music access. Development purposes, obviously you can do a lot of pieces, but certification will take validation that this flow is being done correctly to the satisfaction of ourselves and the music providers. As I mentioned before, another key thing to think about is this is going to change. Alexa is going to get smarter, which means she's going to be able to do more. So as she has more capabilities, new directives might show up. You could have directives, around capabilities you don't even have, new services or new components in the architecture that you don't have support for. It really is important that you write the code in a way that allows you to drop unknown data on the floor, unknown directives on the floor. We're very careful to make sure we do an additive approach when we expand the API as we add new things. We want to add new capability, which allows you to ignore new data that might be coming through, but you can't assume any order about the messages. You can't assume you can assume that the fields you need are there, but if you get more fields than you need, learning to drop those is important. That's a key component in terms of defensive coding is the way I'd call it. And of course, we can add data to formats over time. Taking it away would not be advisable, but adding it will definitely occur, and so you'll see new data. That's obviously stuff we'll provide documentation for. You'll be able to make that change to your code over time, but we know that it'll definitely something you have to think about, how you then work that work in, but making sure you don't break when that new stuff arrives. And of course, this brings a critical point. No matter what device you're building, having an OTA, over-the-air update mechanism is going to be key. It's going to change. Things are going to be improved over time. You definitely want a mechanism that allows you to grow and expand the platform over time. So the next thing is, of course, to take a phased approach. I think a lot of folks jump into I'm going to do it all in one go, and they want to do it all at the same time. But really thinking about, if I were building a new device or a new AVS integration, the first thing I'd really think about is, how do I port that sample? How do I take that Java sample app and what it teaches me, and then port it to my platform? I might have to switch from Java to C++. I might have to switch from Jetty to OKHTTP. I might have to tie in different native components, a different media player, for example. The next is then to think about hardening that around a tap-to-talk solution or a push-to-talk. What are the things that you want to tune around in terms of performance, responsiveness, making sure you're doing the streaming of the audio up properly, making sure you're getting good responsiveness in terms of when you click that button, it quickly responds and has a good user experience itself. Responding around distance testing, testing with different audio outputs, ambient noise, making sure you're getting all those things sort of thought through. And then at that point, now you start thinking about, what's that full hands-free solution look like? How do I then add on this magic of, I want to talk to it from 10, 15 feet away? And there's definitely a lot to think about there, and we'll talk about that in a second. But that's definitely another add-on. So you'd want to take that as kind of a phased approach from a development perspective. And that's where the development kits come into play. So our real goal here from a development kit perspective is we recognize that having the API and an endpoint for you to talk to is very useful, but there's still, a significant effort involved in building out that sort of front end, if you will, the on-device capabilities. What's the right mic array? What about algorithms for, cleaning up the audio? What about, voice processing solutions? What about, different mic array configurations? And so really the goal here is to help close some of those gaps, make it easier for you to pick products and commercial grade products that you can then tie into your platform. We're looking at the dev kits, will continue to grow over time, just like the rest of the platform does. Things like, client software solutions, pre-existing chipsets, voice processing algorithms for, say, echo cancellation, noise reduction, service APIs. This is the best way to really give you access to something that's going to accelerate that, because audio processing may not be the focus, of your company or your device, and helping you get those things faster is definitely the goal. So this is, the idea behind our reference kit platform. And actually, I'll talk more about an example of that in a minute. But several things are required. You really should think about it from a component sourcing and from a testing perspective, really planning on, definitely well over 3 months in advance for tuning, just because there's a whole bunch of components to think about in terms of how those mics, sit in your device, how that will change the audio format, how it's going to deal with, say, barge in or ambient noise. And so we have several partners listed today. That's obviously a list we want to get to expand over time. From a wake word engine perspective, so listening for the word Alexa, Sensory and Kit.ai are our current partners. And then from a front-end hardware perspective, we have Connexent, who provides a 2-mic array with a dev board, and then Intel provides some solutions as well with their own mic arrays and DSP solutions. Big pieces that I mentioned as we talk about that front-end architecture are really obviously that mic array. Echo cancellation is the process of subtracting out the noise you're making. So if the speaker is playing music, subtracting that music out of the mic array input, so you're actually getting cleaner audio. A wake word spotter, which is listening for the device name Alexa. Beamforming, if you have 7 mics like the Echo Dot does, picking the best mic for the source is the idea of beamforming, determining which one's best, and there's algorithms around that as well. And then noise reduction is dealing with ambient noise. So you're in a noisy environment, you're in a kitchen, pots and pans are banging, dealing with removing that audio or that noise interaction from the stream to clean it up. And noise reduction, I should note, is specific for an ASR. So you can do noise reduction algorithms for human ears, or you can do noise reduction algorithms for speech recognition. ASR noise reduction algorithms are actually different than the human ear ASRs. So you do want to think about sourcing ones that are targeted at the ASR options. And so one example of some dev kits that we're kind of hoping folks will use and build from. One is the Raspberry Pi, which is kind of I would target as more of an entry point hobbyist experimentation layer. It actually does have in our Java sample app a wake word engine based on Sensory and Kit.ai. You could choose each one. The example on the GitHub project actually has a very small, microphone condenser mic that you can plug into the USB port, and then off you go. So really very simple, great way to start getting developing, a solution, experimenting, tying into your own custom skills on top, and building kind of a prototype, if you will, around the platform. Very simple. There's a whole walkthrough on GitHub on how to do that. There's also for maybe more of a commercial grade product, Connexent in conjunction with Sensory works on. There's a Connexent 2-mic dev kit for AVS. And that is the board you see there, which has a DSP solution, the whole suite of front-end audio algorithms for echo cancellation, noise reduction, beamforming, as well as even supporting barge-in. And then that particular example, their demo and their interaction ties into a Raspberry Pi over USB for the rest of the client code. But there you have the option of seeing the 2-mic array that you see down below. Anywhere from 30 millimeters to 120 millimeters distance, so you can see how you have a lot more flexibility in terms of placement, how it might fit into your product. It gives you a pretty good commercial grade entry point for prototyping and development. And so obviously there's a lot more options here. There's a lot more things to do. This is just obviously a great entry point for you, and hopefully I've highlighted some of the key things to think about in terms of how you want to build that. At this point, I think we'll definitely want to jump in and see if there are any questions that came in that we want to answer along the way. Ted, any questions that came in?
Yes. Thank you to all the attendees for sending in the questions. We got a ton to go through, so I'm going to just pick a few and Matt, answer them the best that you can. One question from Ben. What does it cost to use AVS? Is there a service fee, license fee, or any royalties associated with the service?
Yeah, so using AVS is actually royalty free. So effectively, the words that everyone likes to hear are free for that. Obviously, we have terms of service around usage. So using AVS, you do need to obviously call our APIs. The device, and the name that you might use for wake words is Alexa. There's a whole bunch of terms of service components, but there's no cost for you. And part of that obviously is to help you get started and innovate, and also you're going to tie into that whole ecosystem of products and services as well. So we're trying to actively, obviously, encourage development of new third-party products. So making it available free for use is definitely a way to encourage a lot of innovation and activity. So.
Great. We had one question from Gregory. When you say that these scenarios, this was further back in the presentation, are optimized for handheld or between 5 to 20 feet, are you referring to user experience, or does that include technical considerations such as noise filtering? Yeah, so optimized for 5 to 20 feet, it really is about user experience. Is the way we think about it. So when we look at products that we're, customers or partners are building to release in the market, one of the things we do look at is a certain amount of wake word testing. And what we want is an experience that is consistent and as far out away from the device as you can get it. So if it's 5 feet away, you can handle a noisy room and still wake up consistently, not have false wake ups, things like that. That would be how we'd kind of, if you will, rate that. Now, what you choose to do, you may say my device is targeted at a close scenario. It's for a device that's sitting on a table and I'm at that table, so it's less than 5 feet. And we'd rate that and look at it from that perspective. That may be right for that product and that industrial design. Whereas others may say, no, this thing's going to be in the corner of the room, far, far away. Therefore, it has to work. So we'll work with you on that in terms of understanding what your targets are, and then we'll help you get to the customer or user experience that sort of is consistent or near consistent with what we see in the Echo family for that user experience you're targeting. Great. One question from a viewer, Khaled. On the custom device, are all requests handed over to the developer for further processing? What level of control does the developer have after speech has been processed?
Yeah, so you actually stream us raw audio. In fact, in our terms of service, it talks about not caching or storing that audio. So you actually pass us, as the user audio travels into the microphone, you then capture that raw audio and then send the stream directly to the voice service. You don't see that audio again. It doesn't come back. You'll see from the Alexa voice service, the directives that you should execute. So play, next, pause, mute, stop, things like that are what you're going to get back. You're not going to see that raw audio, and that's an important component of how customers interact and think about Alexa. They're speaking with Alexa, the service, and Alexa, the Amazon platform capability. So that audio is going to Amazon and then captured on our side. You're not going to see that speech being processed. Now, if you were to build a skill on the back end, so you build a custom skill, and so your skill is called Foo. You could say, Alexa, ask Foo to turn on the lights. If you were the developer for the Foo skill, you would see more information because you'd see the intent that the developer actually asked for. And you wouldn't see the raw audio, but you'd see the intent. So you get more information on what the user is asking for in that scenario. But for devices in AVS, you're streaming us raw audio. We're streaming you MP3 back in directives. So you don't get access to that raw audio.
Great. From one viewer, Mara, she asked if there are guidelines for AVS and where she can get hardware and software documentation?
Yeah, so the hardware and software kind of capabilities, expectations are outlined on the developer portal. So if you go to developer.amazon.com/Alexa-voice-service, you'll see more information about the voice service, and there's a whole bunch of docs as well as expectations. Now, as you can imagine from what you've seen in this demo, if you're doing a push-to-talk, which is sort of a physical interaction, so you've reduced the need to be always listening for a wake word, and then you're simply streaming a piece of audio up and down. The overhead is not significant, and that is something why we think this is something you could put into a wide variety of devices. It obviously runs great on a Raspberry Pi, but it could even run, on an embedded Linux inside of a lower-end wireless speaker. So we see that being supported pretty broadly in terms of platforms and footprints you can fit into.
And I believe we have time for two more.
Sure.
One from Nate. Do users need an Amazon account to use the companion app? And by users, I believe customers, consumers. Or can we delegate access similar to the way you can create tokens for S3 and access without giving everyone their own account?
Yeah, so you do need an Amazon account because what you're tying into is a Amazon customer's set of services. Do they have Prime Music? What music services have they linked to their Amazon account? So if you have an Echo today or an Echo Dot, when you say, oh, I have Pandora, you link Pandora to your Amazon account, so the two can interact with each other. And so you do need that user's Amazon account to then have Amazon validate that, okay, they have Prime Music, or they have Pandora enabled, or they do have TuneIn or iHeartRadio, or this skill is turned on, which is all controlled around a individual user's Amazon account. So there's no delegation model like S3.
And last question for today. This one comes from Amanda. What are some common integration missteps devs make with AVS, and how can I avoid them?
Well, I think there's a couple areas that are kind of challenging. One is I think often people sort of jump to the conclusion that it's a simple request response. And I mentioned the HTTP2 model. There are down-channel interactions. There are out-of-bound interactions where companion app buttons can send messages to the device. So number one, thinking about this as a much more connected and more dynamic interaction than just a request response. Two, I think the audio player interaction, there's a whole state diagram on audio playback. That applies not just to audio, but it also applies to listing out to-dos and your shopping list, right? The sort of the multi-pass play directive model is something to look at, and that's something where often people don't realize that that's audio player model applies not just to music but other areas of the platform. And then I think the third is really sort of the authorization, authentication, that piece. There is before you can really use AVS, you do have to start with kind of the login with Amazon model of either an Android or iOS app or even a web app that generates a token for that first access. So you have to kind of start there before you can get really into AVS, and that's technically another service by Amazon. Not in the same team, but certainly something you have to get through, and so that can generate some early questions and challenges. So I hit those big three, and then beyond that, I'd say using that Java sample app as a guide is definitely key.
Thanks, Matt. Thank you to everyone for attending today's webinar. To learn more about building voice-enabled devices with the Alexa voice service, you will all receive a follow-up email within 24 to 48 hours with a link to review a recording of today's webinar, and the recording will include both the audio and the slides to answer some of your questions. If you have any additional questions that we were unfortunately not able to answer today, please visit the AVS forum. We put that in the chat link to your right. On behalf of the Alexa team at Amazon, thank you for joining us today, and have a great rest of your day.